Today we're going to be looking at section 5.2, which is on evaluating and graphing polynomial functions. And that's what our goal is today. Our goal is to evaluate a polynomial function, and then we're going to be graphing other types of polynomial functions. Now, we've talked a lot over the last couple of years about graphing linear equations and also graphing quadratic equations. Well, we're going to talk today about graphing other types of functions. Okay, they could be third degree, fourth degree, fifth degree, whatever it is. We're going to look at what the general rule is and how to do that. Okay, so first of all, we're going to talk about a couple of terms once again. And a polynomial is a monomial, or the sum of monomials. Poly again means many. Nomials is numerals or numbers. So a polynomial function is a function in this form. All right, so this is the standard form of a polynomial function, where it says a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus on and on and on, until we get to a sub 1 times x sub 1 plus a sub 0. Where a is not equal to 0, the exponents are all whole numbers. Okay, so they're all whole numbers again, which means we can't have negative exponents. And the coefficients must be real numbers. So the coefficients, again, is the number in front of our variable. So the coefficients must be real. So in this general form, the leading coefficient is going to be a sub n. The degree is going to be n, and the constant term is going to be a sub 0. So again, if we have this in standard form, the leading coefficient is always going to be your first number, your number out in front. The degree will always be the exponent of that first term, and the constant term is always the number at the end without a variable part. So some of the common polynomial functions we're going to be looking at, if it has a degree 0, it's going to be called a constant, and it will be something like this, just 5 or 12, whatever, some number. If it's a degree 1, it's going to be called linear, and these are what we've talked quite a bit about. You know, general form is y equals mx plus b. And so here is a first degree polynomial. Second degree polynomial is called a quadratic. Again, these are ones we've talked over and over about. We've graphed hundreds of quadratic equations over the last couple of years. And again, standard form is ax squared plus bx plus c, so if it's in that form. Now the third degree polynomial is going to be called a cubic. And notice here we have a degree 3, and it could be ax cubed plus bx squared plus cx plus d. But as long as it has a degree 3, it's going to be cubic. And 4 is a quartic. And so here again are the standard forms. Here is the example of one. So it's f of x equals something with a fourth power. So when we come down to example 1, we have 4 problems here, a, b, and c, and d. It says identify the polynomial function. We want to decide whether the function is a polynomial function or not. Okay, so that's our first step. Decide, is it a polynomial function? So we're going to look at this one. Does it meet the criteria? And this one is no, because we have an exponent here that's a half. A half is not a whole number. Remember, our exponents must be whole numbers for this to be a polynomial function. It's not. So this is not a polynomial function. In example B, is this one? Well, let's look at our exponents. 5, 2, 4. Those are all whole numbers. Okay, let's look at, remember, polynomial function. The exponents are whole numbers. The coefficients are real numbers. So real number, real number, real number, real number. Okay. All of the numbers in front are real numbers, so this is a polynomial function. All right, so now it says, if so, write it in standard form. So let's do that. We're going to go g of x equals, now standard form means I want my highest power first. My highest exponent's going to come first, then so on and so forth. So it's going to be g of x equals negative 8x to the fifth plus x squared minus 4x, plus, wrote that wrong, plus x to the fourth minus 4x squared plus square root of 10, which is my constant. There's no variable part on that. That is my constant. So we wrote it in standard form. We state its degree. Well, what is the highest degree? It's 5. Now we don't have a special type for this one because we don't have one. It's not one of those that we have up there. So we're just going to say that it's a degree 5. Don't worry about the type in this case. And then the leading coefficient is going to be negative 8 because that is the number in front of our highest exponent. So down to letter C, to example C, we want to check this one. Is this a polynomial function? Exponents, good. They're both whole numbers. The numbers are leading coefficients. 1, negative 4/5, negative 1. Are they real numbers? Absolutely. So this one also is yes. It is. And let's write it in standard form. Well, it just so happens that this one's already in standard form. So we're just going to rewrite it in the way that it is. And the degree is a third degree, which makes it a cubic. Okay, right here we have third degree, so therefore it has to be cubic. So the type is cubic, and then its leading coefficient is 1. And so that's what we have there. And then if we look at D, it says h of x equals negative 3x to the fourth minus 9x to the negative second. Again, that is not a whole number, that exponent, so therefore this is not a polynomial function. Then we're going to jump down to example 2. It says evaluate by direct substitution. This is something that you have done numerous times. It says use direct substitution to evaluate f of x when x is 2. So here you are going to put 2 in for everything. So I want to find really f of 2. So I'm going to go negative 3 times 2 cubed plus 2 squared minus 12 times 2 minus 5. And I want you to make sure to leave it as f of 2. Put your answer in that because that's our input value is 2. Then we want to find out what our output value is. Well, 2 cubed is 8. 8 times negative 3 is negative 24. So we're going to have plus 4 minus 24 minus 5. And if we add those up, we are going to get negative 49. So there is our answer using direct substitution. We put in 2, we get an answer of negative 49. So I would like you right now to go ahead and do questions 1 through 5. It says decide whether the function is a polynomial function for 1 through 3. If so, write it in standard form, state its type, degree, and leading coefficients, and then use direct substitutions for 4 and 5. So go ahead and hit pause on the video, and then you may hit play when you are ready to move on. And here are the answers to questions 1 through 5. So go ahead and check your answers. The next thing we're going to talk about is something a little bit different. It's going to be related to questions 4 and 5. Like we used in questions 4 and 5, we use something called direct substitution, where we plugged that in directly to each of those parts. Now, the next thing we're going to talk about is something called synthetic substitution. And this is a method used to evaluate a polynomial function. So here's how it works. We're going to take and evaluate this polynomial function using synthetic substitution. So here's what you do. You take and you write the coefficients down. So it's going to be negative 3, 1, negative 12, negative 5. You start with the highest one, and you must have every column filled. So here, this was a cube, the squared, the x for the first, and then the constant. So I have those written down. If you would have been missing a column, you have to put a 0 there. For example, if this was not here, you can't just skip from the x cubed to the x. You'd have had to put a 0 in there for that column if it doesn't exist. Okay, and we'll have one like that in the guided practice, so I just want you to make sure that you do that. All right, so now what we're going to do is the same thing. We're going to put this in. Okay, so I'm just going to write the 2 out here. And then we're going to zip through this. So here's how it works. I'm going to bring my negative 3 down. Now I'm going to multiply these. 2 times negative 3 is negative 6. Then you add. 1 plus negative 6 is negative 5. Then again, you're going to take 2 times negative 5, and you're going to get negative 10. Then you add. So that's negative 22. Now you're going to take the negative 22 again times 2. That's negative 44. And then you add. So that's negative 49. So your answer is f of 2 equals negative 49. So again, here is the number that you put in. Here is the number that you get out for an answer. All right, so we're always adding vertically, and you're always going to multiply the number down here by 2, or the number out front. So that's what we're going to be looking at when we do synthetic substitution. So right now what I would like to do is I want to jump down to the guided practice questions number 6 and 7, and we'll go back to talk about what we skipped there. But I want you to do questions 6 and 7 using synthetic substitution. All right, so go ahead and try questions 6 and 7. Hit pause on the video until you get those done, and then you can hit play when you are ready to move on. And here are the answers that we get when we do questions 6 and 7. All right, and again, remember, we bring down the 5, then we're going to take our 5 times 2, which is 10. That goes here. Then we add them up. 3 plus 10 is 13. Then we're going to multiply our 13 times 2, which is 26, which goes here. And you add them up, you get 25. Then you're going to take your 25 times 2, which is 50, which goes here. And then you add them up, and you get 57. So here you have f of 2 equals 57. And the same thing over here in example 7. Now, notice, here we had x to the 4th, x to the cube, and then x. We did not have an x squared term, so we're missing that one, which means you have to put your 0 in that spot. You have to have, if you have an x to the 4th power, you have to have 5 columns. If you have an x to the 8th power, you have to have 9 columns, because the last one is for your constant. So always remember that. You have to fill every column starting with the highest degree. And so then you put your numbers in, you get g to the negative 1 equals negative 10. So that is using synthetic substitution. Now, sometimes synthetic substitution is way quicker and way easier than direct substitution. Sometimes direct substitution is going to be much easier. So depending on what type of problem you have, whether you should use synthetic substitution or direct substitution. All right, so that is how to evaluate polynomial functions. So that was the first part of our goal, was to evaluate some of those. Now we're going to talk about graphing those. So let's go back to the notes to where we were before we skipped ahead, and that is on end behavior. So the end behavior is the behavior of a graph as x approaches positive infinity or negative infinity. For the graph of polynomial function, the end behavior is determined by the function's degree and the sign of its leading coefficient. Now, the best way to look at this is to think of the types of graphs that we have dealt with in the past. And the first one is going to be linear. We've talked about a lot of linear graphs. And linear are odd functions. And the reason is because their degree is 1. Okay, so when we talk about degree of a polynomial, we're talking about odd functions if it is a 1. So all the linears are 1 because it was y equals mx plus b. Well, there was no exponent there. The exponent is a 1. So if we had a positive slope, we knew that our linear graphs look like this. If we had a negative slope, we knew that the graph looked like this. The same thing is going to be true for all odd functions. If it has a positive slope, so if the degree is odd and it is positive, meaning our leading coefficient is a positive number, the end behaviors are exactly that of a line that has a positive slope. So I'm going to have an x up here and an x up here, and that's what I'm going to talk about, is that's where my end behavior, my graph goes to. It's going to go up to positive infinity to the right and down to the positive infinity to the left. So a graph could look something like this. And whenever I graph these, you're going to always see me put a little x on my graph so I know where my end behavior is going. Because then as I plug in ordered pairs, which we're going to be doing, once it starts getting really big, I know, oh, it's going to keep getting really big, and so I don't have to put in any more numbers to that side. The next thing that we are going to be talking about is if it's negative, I know that it goes down to the right. So again, my graph for these odd functions is going to look something like that. Now, when we write this, we're going to write some statements in here. So we're going to say that f of x, and this means approaches positive infinity as x approaches positive infinity. Oh, not a positive infinity. What that means is this: as x goes this way, as x gets bigger, y is getting bigger. And down here, we're going to say f of x approaches negative infinity as x approaches negative infinity. Because as x gets smaller, y also gets smaller. The same thing is true on the other side. Here, f of x, or which is my y value, approaches negative infinity because it's getting small as x approaches positive infinity. So as x gets bigger here, y is getting smaller. And the same thing is true on this one over here. We're going to say that f of x approaches positive infinity as x approaches negative infinity on that side. Because again, as x gets really small, y gets really big. So that's what we're talking about when we talk about the end behavior of odd functions. Odd functions means your exponent's going to be 1, 3, 5, 7, 39. Okay? Whatever that is, whatever that degree is, if it's an odd number, then it's an odd function. So your end behaviors are going to add, or are going to be away from each other. Either one's going to be up and one's going to be down, or one, on one side to the left or to the right. So it's going to follow the same. Well, it's going to look like a line where your end behaviors are at. Okay, one's going to be up, one's going to be down. We might have a whole bunch of different squigglies and maximums and minimums, in between, or local maxes and local mins in between the end behaviors, but that's where they're going to go. Now, the next thing we're going to talk about is something called an even function, or an even degree. And when the degree is even, like our quadratics, which is what we're going to compare all of this stuff to now, our quadratic functions, we know that either it opened up or it opened down. So that means both of our end behaviors are going to either end up being up, or both of our end behaviors are going to end up going down. And so that's what we're talking about when we talk about any degree that is even. So whether it's an x squared, an x to the fourth, an x to the 6, an x to the 12th, an x to the 300th, it doesn't matter. If the degree is even, they're going to end up in the same spot. Well, when we talked about the quadratics, if it was positive, we knew that the parabola opened up. So my end behavior, if it's positive and even, means it's going to end up going up. So my graph could look something like this. And then obviously if it's negative and it's even, they're going to end up going down. Again, notice I put my x's where they're going to be, and so this one is going to go down. So when we look at the end behaviors, we're going to say again that f of x and this y value approaches, it's going up, so it's positive infinity as x approaches positive infinity. And here, f of x also approaches positive infinity as x approaches negative infinity. Okay, so as x gets really small, y gets really big. On the right side, as x gets really big, y gets really big. And in the even and negative here, f of x approaches negative infinity. It's getting really small as x approaches negative infinity. And here, on the right side, f of x approaches negative infinity as x approaches positive infinity. All right, so once again, as a recap of that, if it's odd, you're going to have split. One's going to be up, one's going to be down. If it's even, they're going to be together. Okay, so we want to look at graphing some of these using what we know now about things that we've talked about. So if we look at example 4, it says standardized test practice. What is the true about the degree and the leading coefficient of the polynomial function in the graph shown? Well, we know that the end behaviors here are both going down. So if they're in the same spot, automatically we know that it's even. Okay, so this is even because they're both in the same spot. They're both down. Well, if they are both down, then we also know it's going to be negative. So this one is even and negative. So the degree is even. The leading coefficient is negative. So it has to be D. All right, so example 8, guided practice, question number 8. I want you to answer this one. Describe the degree and the leading coefficient of this polynomial right here. So go ahead and pause the video quickly until you get that one, and then when you are ready, hit play. And the degree for number 8 is odd because we notice that our end behaviors, we have one down here and one up here. They're not on the same side. So one is up and one is down. So automatically it has to be odd. And then it goes up to the right, so it is positive. If it would go down to the right, then it would have been negative. So when we graph these polynomial functions, which is the second thing that we want to do now, is we're going to graph these. We're going to plot the points to determine the shape of the graph's middle portion. And we're going to use what you know about the end behaviors to sketch the graphs of these. Okay, so here's what I'm going to do first. I'm always going to start by looking at the degree and the leading coefficient, and I'm going to put little x's on my graph so I know where the end behaviors go. Well, this one is even. Example A is even because we have an exponent of 4. So I know that they're going to either be both up or both down. They're going to be in the same spot. and it's negative, so I know they're going to be both down. So I'm going to put little x's on my graph here. There we go. There's where my end behaviors are. Now, all you're going to do is plot some points. So what we're going to do is we're going to make a table of values. And I know if I put in 0, I'm going to get 6. Using direct substitution, that's what I did. All right, now let's go ahead and put in some other numbers. Well, I'm going to use synthetic substitution. So I'm going to go -1, 4, -1, 0, 6, because if we see that, there is no x term, so I have to have my 0 in there. All right, so let's put in 1. So this is going to be -1, -1, 3, 3, 2, 2, 2, 2, 8. So it's going to be 1, 8. And so if I put in 1, it's going to be 8 up here somewhere, and it's going up. Do I need to put any more to the right? And the answer is absolutely I do. Because I know that this graph has to come down to here. The end behavior is going to be down. So I need to keep going until I can see for sure that that is going down. So let's put in 2. All right, so now we're going to put in 2. And again, synthetic substitution works really quick and really easy to do this once you get the hang of it. -1, so this is going to be -2, 2, 4, 3, 6, 6, 12, 18. So if I put in 2, I'm going to get 18. And again, that's continuing to go up. So 2 is 18, and I'm just going to put some points in up here. Again, I have to keep going because I know that it's got to come back down. My end behavior tells me it has to come back down. So I'm going to put in 3. So that's going to be -1, -3, 1, 3, 2, 6, 6, 18, 24. So if I put in 3, I get 24. Again, that's continuing to go up. But it's not as much. So hopefully we're getting to the point where we're going to start coming back down. Let's try another one. You got to keep going until you find that point where you can be confident, oh, it's going down and it's not going to turn around. So we're going to put in we're going to put in 4. So we get -1, -4, 0, 0, -1, -4, -4, -16, which is -10. So if I put in 4, I got -10, which is way down here, and I can honestly, or I can be confident that I know that this, once it gets up to that point and gets down to -10, there's no coming back. So it's going to look something like that. So now we have to go to the other side, because I know that I have to get down to this end behavior down here. Once I get to that, we can be confident that we're done. So again, we're going to pick some numbers on that side and go from there. So -1. This is going to be -1, 1, 5, -5, -6, 6, 6, -6, and 0. So we're going to at that point, -1, 0. Well, it's going down, but we're going to probably need one more point just to make sure. So let's try -2. So this is going to be -1, 2, 6, -12. That's -13. This is -20 or +26. 26 times -2 is -52, and I can see that that's going to be a negative number. So I know that my graph is going to come down like this, and there would be the graph of that function. Right? So the biggest thing is to find the end behaviors, and then you're just going to plug in a bunch of points. Now, this one obviously was a little bit more complicated. We had to put a bunch of numbers in. So let's look at example B. In B, we're going to do the same type of thing here. We're going to find the end behaviors. Now, notice this one is an odd number. So odd means we're going to have one up and one down. So then you look at the leading coefficient. It's positive, so it means it's going to go up to the right. So my end behaviors are going to be here and here. So that's what my graph's going to look like in this case. So now we start putting in numbers. And I'm going to put in 0. I'm going to get 1. All right, so you can make your table of values. So if I put in 0, I'm going to get 1. Now, in this case, I might use direct substitution because I have numbers in here that might be pretty easy to work with. So if I put in 1, I'm going to get 1 minus 3, which is negative 2, plus 1, which is negative 1, plus 1, which is 0. So now I'm going to put in 2. Well, that's going to give me 8 minus 12 plus 2 plus 1. So that's going to give me so that's going to be negative 4 plus 2 is negative 1. Wait, did I do that? What did I put in? Yeah, so that's going to give me a negative 1. So then you can put in your 3. And again, you can use either direct substitution or synthetic substitution. But 3 squared is 27. 9, so that's minus 27 plus 3 plus 1. So if I put in 3, that will end up giving me 4. And that one's going up toward its end behavior, so I'm done on that side. It's not going to come back down. So now let's put in some negative numbers. If I put in negative 1, that's going to be negative 1 minus 3 minus 1 plus 1. So that's going to give us negative 5 plus 1, which is negative 4. And that one is also going to its end behavior down here. So there's your graph on B. All right, so turn your books to page 340. We are going to look at example 340 out of your book, and we're going to walk through that one a little bit. So make sure to get your books open to page 340. If we look at page 340, they say graph the function f of x equals negative x cubed, or no, the energy problem, we're going to say the energy E in foot-pounds is going to be equal to 0.0029 s to the fourth. Now, in this case, it's a real-life situation. However, we're only probably going to be concerned with the numbers in quadrant 1 because it doesn't make any sense for us to talk about problems that are where any of these variables are going to be negative. So if I put in 0, I'm going to get 0. Okay. If they make a table of values for us there, and so we want to go from 0, 10, 20, 30, 40. And then the values that they give us when they plug those in. So we're going to go up by 500s here. I'm going to go 1,000, 2,000, 3,000, 4,000. And so if we plug in 0, we get 0. If we plug in 10, we get 29, which is obviously not very high. But if we plug in 20, we're going to get 464, which is just under our 500 mark. If we plug in 30, we're going to get 2,349. And if we plug in 40, we're going to get 7,000. So that's way off our graph. So here, our graph is going to look like that. And so they say graph the model, which we just graphed. Use the graph to estimate the wind speed needed to generate a wave of 1,000 foot-pounds of energy per square foot. So then if you look at that, you're going to go on your graph over to 1,000. And you're going to try to figure out, my line is a little bit crooked here, where that matches up. And it looks like we're just shy of 25, so we're going to call it about 24. And if you look at their graph, that's what they ended up with, a wind speed. So the wind speed would be about about 24 knots. All right, so what I would like you to do right now is to try questions. We'll go ahead and try to graph questions 9, 10, and 11. Go ahead and hit pause and then hit play when you are ready. And here are the graphs of 9, 10, and 11. Again, notice number 9, positive and even, so they both open up, and behaviors. Number 10 and 11, they're both odd and negative, so they're both going to be split. One goes up and one goes down. So again, when we graph these polynomial functions, the two things that you have to do, and that's it. Find the end behaviors. Like I do, I would recommend marking them on your graph, like I do here with the blue X's, the green X, and the red X. Mark where your end behaviors are going to go. Then you just plug in some points to see where it is in the middle of your graph. Okay, so again, this section is on evaluating polynomial functions and then graphing polynomial functions. So those are the two things that we're looking at, and here is your homework assignment, set 1 or set 2 for section 5.2, which is on evaluating and graphing polynomial functions.